So welcome to this session on irrigation management advancements and measuring evapotranspiration and crop water demand. This session we have 4 speakers, and we are going to be examining these technologies and how they're being used. So our first speaker, so what we'll do is we'll have the 4 presentations, and then we'll invite the speakers to come up and answer questions from all of you. Does that sound okay for everyone? So our first speaker is Dr. Daniele Zaccaria from University of California, Davis. And he's an expert in irrigation and works with research and extension there, right? So Daniele, please come and let's welcome Daniele, right? Daniele got his PhD at Utah State University. He's originally from Italy, right? The southern tip of the boot, on the heel, right? The heel of the boot, right? So, okay, Daniele, you've got the floor.
Glad to be here today. Thank you, Christopher, and the organizing committee for having me here. I'm going to give you some preliminary results today about a couple of projects that I've been leading in the last 3 to 4 years, and they were aimed at appraising the inaccuracy and errors of satellite ET estimate for citrus in and pistachio production orchard versus ground-based measurement. What I'm going to do today is giving you a little bit of background information about citrus and pistachio production in California. Those are large commodity. They generate a lot of value and income. And then we'll touch a little bit upon the methods that I use for ground-based ET measurement and satellite remote sensing ET estimates on those production orchard. And then we'll illustrate some comparisons and the findings from the comparison between the 2 data sets. And then I'll provide some conclusive remarks. I want to make sure that everybody understands here that I'm talking about preliminary data and findings, so those are not finals, and those are drawing from UC, University of California Research Studies that I'm leading, but the methodology and the final conclusion still need to be peer reviewed, so I'm providing today a state of progress of our projects, okay? Of course, this is the work of a large group of people that are collaborating with me. Those are my lab members at UC Davis. They're experts in ecophysiology, stress physiologists, and biometeorology. So it's not my work only, but it's the work of a large team of collaborators, and I'm presenting the results from 3 years of work. Okay. First of all, some facts about citrus. We got a large acreage in California. It's about 270,000 acres. Most of it is bearing acres, so they bear fruits already, and a little bit of replanting. And so non-bearing acres is about 10,000 acres. As you can see, the total production is about 4.9 million tons, and this is almost 80% of the U.S. production. So basically, California is a powerhouse of citrus production in the U.S. The economic value, this is referred to 2023, was a $2.6 billion industry. And this is actually the 5th largest commodity. I made a mistake in the presentation because pistachio is the 4th now. When it comes to distribution and different varieties, you can see basically oranges, mandarins, and lemons are the most relevant varieties, and they spread across most of the state. And so it's really very spread out. And when it comes to pistachio, this is going bigger and bigger, while citrus is about stable in the acreage. Pistachio is growing, and we reach now 600,000 acres. Most of it is bearing acres, and There's a new planting also, about 145,000 hectares on non-bearing acres. So the production is keeps growing. It's about 1.5 million pounds in terms of production. Economic value is $3 billion industry. And this is ranked as the fourth largest agricultural commodity. So I reversed the order. Pistachio as fourth and citrus is the fifth in terms of value generated. This map is 2023, is the location of the acreage. I don't know if you can see it, but it's pretty much concentrated in the eastern side of the San Joaquin Valley where all the water limitations are. And also in the low desert and the area of the coast, Ventura County and Los Angeles County, and it's really, really, very spread out. So you got citrus and wherever you go in that part of the state. Pistachio is even more spread out and is replacing almonds. After replacing cotton, is now replacing almonds because almonds reached saturation on the market. And it's also very much impacted by the drought, and pistachio is now coming into place. So growers are pulling out almond orchard and putting in pistachio because it's much tolerant to drought and salinity, and it's also very resilient. So when the water comes, pistachios start production at potential level again. So for all this reasons is basically growing exponentially. You can see it's almost ubiquitous. But most is a central part of the San Joaquin Valley, southern part of the San Joaquin Valley. All this intensive production area sits on overdrafted aquifers. And so here there's a problem in water limitation, either from the physical drought or from the environmental water limitation that are related to groundwater. The groundwater management regulation is called SGMA. And so all these two factors together, either the recurring drought or the environmental water regulation, are really calling the question if there is sufficient water to maintain the citrus and pistachio production acreage. I have to rush. Anyway, the context is that a lot of water districts and GSA, which are the groundwater sustainability agency, adopted satellite remote sensing models in order to estimate the crop ET. But the problem is that no work was conducted before adopting these models for accuracy assessment. So the accuracy of satellite remote sensing of ET was just assumed based on paper and work done in other states. There are multiple errors with satellite remote sensing, and we are at the level of 15 to 60% overestimate or underestimate on orchards and vineyards. So this is a large inaccuracy, and mostly due to the physiologic response of the crop with respect to the weather parameter. There's also a problem of coarse pixel resolution. 30 by 30 is mostly the satellite pixel resolution from Landsat. And this doesn't allow to separate the soil background from the canopy. But also there's a mechanism to infer the daily ET from an instantaneous snapshot when the satellite overpass around 10 or 10:30 in the morning. So you get a snapshot, and from that snapshot, the daily ET is inferred. And in this process of calculation, there's no consideration on how the crop regulates its transpiration during the day. Also, you got one overflight every either 8 days or 16 days. And so if you have an error at that moment, that error is propagated for 8 days or 16 days. And so there's a huge gap filling with this method to be done. So all this, leads to often inaccurate orchard ET estimate. And those are coming into play when their water allocation and also the water districts are charging growers with penalty fees if they use too much water with respect to the allocation. But allocation and penalty fees are based on a satellite, not really flow meter reading. And so this is putting a lot of risk in terms of profitability and sustainability, economic sustainability of the production. So we started 3 years ago, actually 4 years ago, with under solicitation of the Citrus Board. The Citrus Board, California Citrus Board, wanted to have an independent evaluation of the OpenET, which is an open platform for satellite ET estimate. And then we expanded the work on pistachio, almonds, and wine grapes with other commodity boards. And of course, we are comparing ground measurement from flux towers with respect to OpenET estimate. The OpenET platform, I don't know if anybody is familiar with that, use satellites, Sentinel and GOES. GOES is a geostationary satellite. And spatial scale is about 30 by 30. So a 30 by 30 meter is at 0.22 acres. This is a pretty coarse for the micro-irrigated orchards and vineyards that we have in California. And we got from daily, monthly, seasonally, yearly estimate. Their OpenET includes like 7 models. 6 of them are indicated here. Those basically physical models. Seaball Metric, Dysalexis, SS EBOP, Priestley Taylor, Jet Propulsion Lab, and SIMS, or top SIMS. And they use different algorithms. The first 3 use a residual energy balance with optical and thermal multispectral, thermal bands from multispectral images. The other one use a simplified assumption or reflectance-based crowd coefficient. There's a 7 model that is spitting out the outlier, considering the 4 mostly use the closest value, and it spits out the outlier, and then he averages out the 4 closest values. Okay, this is called OpenET ensemble model. What we do on the ground, we use the residual of energy balance. So we basically determine ET as LE from the other measurements. So we measure net radiation with the net radiometer. We measure ground heat flux with the soil heat flux plates, a soil temperature probe. And then we do sensible heat flux, actually, with 2 parallel methods. One is eddy covariance, and the other one is surface renewal. But we use mostly eddy covariance, and when we have data gaps, we use calibrated surface renewal to fill the data gaps. We complemented all this measurement with temperature and relative humidity in the orchard, solar radiation, fine wire thermocouple, and infrared thermometers. Of course, there's quite a bit of disturbance at night. We're not alone in the field. There's always some presence, so we notice some disturbance. And so here, one of our guardians, but there's a lot of nightlife in the orchard, especially when there are rodents. And you can see here, big birds sitting on a 3D sonic anemometer. And so we put some protection there in order to avoid this disturbance. And the guy likes the foot massage there anyway. So the problem is now solved. We just get rid of those data when they're inaccurate. So page Mandarin, I'm presenting some results. Page Mandarin, we got east-west and north-south block in the San Joaquin Valley. Here's a few characteristics of the orchard. Canopy cover, refraction canopy cover is about 70%. You can see some picture there, how it appears. I wanted to show you here, this is a normalized root mean square error difference on a monthly basis between measure ET from the ground and model ET. And you can see east, west, north, south. The orange is measure and the blue line is model. And so you can see the different years. We got from 15 to 35% difference, 20 to 50, depending on east, west, or north, south. But I'm going to give you some snapshot of the result that we got. And mostly the metric model overestimate what we got on the field. This is a Seaball, one of the most used model from the water district. You can see the discrepancy is even larger here, 20 to 60%, 20 to 55%. And moving forward, when then the outliers are taken out and OpenET ensemble values are considered, situation doesn't improve so much. And so you got a big difference between measurement and ET estimate from the satellite. When we put all the data together for the amount of years that we have available from the ground, you can see here the normalized root mean square error on the left, on the y-axis, and the years, and these are our seasonal root mean square error. And there's quite a bit of overestimate by the satellite remote sensing. All the satellite remote sensing of ET model overestimates citrus. When we normally go to the field on a periodic basis and we measure stomatal conductance with the portable photosynthesis system, in order to understand where those overestimates error come from. And so you can see here the stomatal conductance we measure every 2 hours on specific days. And you can see citrus, start high during the day and then it shuts down the stomata. Basically, after around 9 to 10, it closed the stomata, and so evapotranspiration is over at that time, and then reopens the stomata at night. And this goes, in tight correlation with the vapor pressure deficit. So when air becomes hot and dry, then citrus, which is a subtropical crop, reduces the transpiration, so go into protection. When we put the things together, you see VPD versus stomatal conductance, then you see the transpiration is high in the morning and then very low in the afternoon and evening. So, and I circle in red there when the satellite overpass occurs in California. So this means that basically a snapshot occurs there, and then daily ET is calculated from that moment, not considering that the crop regulates its transpiration over the day. So that's a big source of errors. I wanted to show you data on navel orange, which is pretty similar, overestimate by the satellite. And you can see a similar behavior on oranges. And again, early in the morning, high transpiration rate, that is inferred as a daily, because the model calculates the actual ET versus the reference ET and consider that ET fraction constant over the day, which is not constant. And you can see where most of the overestimate come from. Lemon is the same. This is the desert, the Coachella Desert. I'm giving you some snapshot. And again, young lemon or mature lemon doesn't really make a lot of difference to rush. So the preliminary conclusion for citrus is the overall, all the model so far that we tested overestimates citrus ET. There's, the overestimate increases as the year becomes drier and drier. This is counterintuitive, so you expect more accuracy when water is short, but this is not happening. Citrus ET overestimate appear to be higher for north-south row orientation than east-west. And the model performed slightly better on mandarin orchard than on orange orchards. I wanted to show you also a ranking of the different models that are included in OpenET. These Alexis somehow perform as the best 20-30% metric ensemble and top sims. Somehow in between 20 to 40%. SSC BOP is a simplified model, 20 to 50, Priestley Taylor 20 to 60, and Siebel as the, I would say, 5 best performing model and probably lowest accuracy on that. However, there's a lot of inaccuracy and inconsistency between years and orchards. I wanted to show you the last slide, and this is about pistachio. So we measure, again, stomatal conductance over pistachio. This is a young orchard near Davis. And you can see in the right graph that the transpiration goes up in the morning, reach a maximum, and then it shuts down the stomata. So pistachio is a desert plant. Citrus is a subtropical. They're completely different. So assuming that all these models are going to have an accurate estimate of ET on completely different species is basically an incorrect assumption. So here I circle again the satellite overpass. And you can see in the case of pistachio that the satellite overpass capture a moment that is low in transpiration, and then transpiration increases over the day, and then it closes down the stomata, which is completely different from citrus that I showed you before. So what we should expect on pistachio, the opposite of citrus, so underestimate. So here it is on young pistachio, underestimate by the models with respect to the ground measurement, and quite a bit of underestimate. So you can see we have non-cover crop and cover crop. So cover crop is also a confounding factor on the satellite, what the satellite sees on orchards and vineyards. You see, here's SIBO. I don't know who can afford that level of inaccuracy in California with the price of land and the price of water these days. So with that, I'll stop here, not to take too much time, but I'll be hanging around. So I'll be happy to entertain any question later on. Thank you so much.
Thank you, Daniele. I hope you hang around.
Yeah.
Speaker is Dr. Mohsen Hafiz. He's the Strategic Program Director for Water, Food, and Ecosystems for the International Water Management Institute, and he's based in Pakistan, right? So please, and he's going to tell us about his experience using eddy covariance towers for measuring ET.
Good morning, everyone. Thanks, Neil, for inviting me here. Okay, so just on. I will be talking about that one, the actual evapotranspiration for the broader irrigation system, and saying it what our initial results are for the flux tower in the Indus Basin, Pakistan. And this work, sorry, just going back. This is the work, teamwork, and I'm presenting it here. We have been working a lot, but flux tower is only 1 year of experience, and I'm sharing the preliminary result what we got it. When we're talking about the Indus Basin, what that brought to common is that one, it's the most climate vulnerable country, it's the largest contiguous irrigation system in the world, but if you are looking around in terms of efficiency, water use efficiency, it's only 35%, and it's already we are facing a lot of problems on that one. If we compare to all the neighboring countries, the water use efficiency is much higher in Pakistan, that water use efficiency is lower. One of the bigger problem is that in the irrigation field, there is hardly any accurate accounting of that one. What's the actual water consumption? And there is a lot more research is needed in that one. Groundwater is contributing much more on that one. 60% is overall, from 20 to 80% groundwater contribution is coming for the irrigated agriculture. But for the urban and urban and industrial, it's more than 90%. Making all those things quite complex, and when you don't have the accurate accounting of the resources, surface water plus groundwater, and there is an imbalance, so often we are facing the flood or we are facing the drought. During the monsoon 3 months, 83% of water comes and we are facing the flood, and the remaining 9 months the water storage capacity is only 30 days for the whole year, and then the whole country is suffering the drought. In that kind of thing, how to make sure that we are able to manage that one, the irrigated system productive. And one of the problem is that one, there is a silo departmental approach. Water is treated separately, energy is separately, agriculture department does not talk with the water department. How to make these things happen? And all on the top of that one, there is a wastewater is being directly injected into the water bodies and also in the groundwater, and that makes the whole situation quite complex on the One Health initiative. Policy incoherence is very common, and all sort of things. What we are doing, that creating a lot of problems in the social conflicts, not only between the neighboring countries. We are facing a problem with India, we are facing a problem with Afghanistan, but also in the riparian provinces upstream and downstream, due to water scarcity and lack of trust on that one. That created a major issue, that one. In order to build the water resilience and then the adaptation to climate change, we are working on various fronts, and I'm talking it today, presenting it on the Flux Tower, what we are doing it. As there is a government institute are now so strong in terms of providing that one, the actual water consumption. So what we are doing it here, we have installed under the FCDO project, which and also the CGIAR Nexus Gain, 6 flux towers, and those are the Lycor flux towers. We set up in a way that one we are talking about agroecological zones as a part of that one, and picking up from the Punjab, which is a food basket, for the close energy balance, which are equipped with all the things which my previous the speaker mentioned about that one, the net radiometer, 3D sonic anemometer, and all sort of things are there. And in addition to that one, we are installing the two more into that, the upper part of KP province, and that will give a really strong footprint of around the 1200 kilometer, where we are capturing all this sort of thing. And then we have recently purchased another one methane emission analyzer, which we are also installing it on the system. And here I'm sharing the one of the snapshot where we have the 3D sonic anemometer, we have a net radiometer, we have a soil heat flux plate, we have also the soil moisture sensors, rain gauge, and everything. And this is showing the snapshot of the mixed cropping system on the field, where we have installed that one, the flux tower. Again, we energy balance closure. Yes, we did it. I mean, this is the snapshot of the daytime values. We have not accounted everything for the 24 hours. It's a daytime. When we are looking around the daytime, what we have got over a year as a period of time, and of course we have put one of these, the research assistant who is looking after on that one, and so we got it the variation from 0.72 R square over the values of that time to the 0.88. That's what the variation which we are getting it, and of course that when we go over the 24 period of time, then there is a much more that when the variation is coming as a part of that one. But here we are looking at around, as our whole thrust is on that, we are looking around the daytime, how we are able to compare it and everything, and that's the. So I'm talking about the four of the examples here. First is about the Akada, which is about the semi-arid zone with the irrigated agriculture, mainly for wheat, maize, potato, and then the vegetables. And these are the cropping season in Pakistan. We have a Rabi cropping season and then the Kharif cropping season. So we applied for the PICE-EVOL. We also applied for the surface energy balance SABs. We also applied for the vapor. Here I'm providing the example of PICE-EVOL, which we have modified and adapted to the Pakistani with a lot of data. And it's again the traditional one, getting all the input parameters, solving the energy balance as wet and hot pixel, the cold and hot pixel, and then solving the energy balance and getting the information at the time of the satellite overpass, converting into the gap fill to that one, the day, and then going to the monthly, and then aggregated to the annual one. And here I'm presenting the results on the monthly basis, which is showing a different picture. When we go on the daily basis, then there are the more variation is coming in terms of ET, but as our interest is about the cropping season, so therefore we are using the monthly basis value as a part. And here on the left-hand side, we are saying that one, the annual actual evapotranspiration, and on the right-hand side, in between, we are saying Kharif and Rabi, and on the right-hand side, we are saying the aggregated product on a monthly basis for various months of the 2024, because the flux towers are functional in November 2023, and we started taking the data from 1st of January when we have a validation. Until now, those are functional. This is showing the snapshot. What that means, we are getting it as a part of that one. Again, we are getting that one. These are the variations, showing it over the period of time. Overall, we are saying that one, the flux towers on average, it's again showing the different trend. During the month of this, when we are talking about the May till, from that one, the month of the January, February, March, it's a bit over, and then that's underestimating, again linking at that one. Overall, when we are looking for the whole year of the cropping cycle of that one, annual flux tower ET is around 10.20 millimeter, 1020 millimeter, and 1005, and the R scale is that one. But we have also installed the soil moisture sensor, and soil moisture sensor is capturing and along with the rainfall when we analyze on that one. On the soil, the time series of soil moisture sensors, not 1, 4, or 5 soil moisture sensors are installed in the neighboring field. That's showing that one, when the irrigation is applied and when the healthy crop vegetation, as well as on that when there is a drought period. And bearing in mind, in Pakistan between May to August, around 70% of rainfall occurs in that month period of time, and that's where you're seeing a lot of one. Also looking around the water use and productivity assessment on a weekly basis. Here we are looking around the GPP, and on the top we are saying that one, for the peak of the one, which is biomass, is at the peak in the Rabi season, it's in the February, March, and then we are saying that when the fallow period between that one, the April, May, and then again the peak in July, August, as a part which is less because there is much more of evapotranspiration, is much more consumption is there. And then again we are seeing a peak of that one. That's showing the end of the Kharif season, Rabi season and Kharif season, capturing those variability and how this could. And also when we are looking at monthly variation between the ET and then the gross primary product and water use efficiency, again we are seeing that when the water use efficiency is highest in terms of the February, March, when there is not high in terms of the demand of the ET, there is more consumption on that one, and then over the period of time, then in May it goes less, and then again in July, August it's a bit higher, and we are seeing a similar trend. Lastly, looking around the gross primary product, which is very important for the the healthy of the production as a part of that one. And again, we are seeing the similar trend in February, March. It's the maximum one on that one, and then there's fallow period where there's not a lot of the the carbon processes are happening, and then again in October, November is the same thing. But when we look around the net ecosystem exchange, which is about that one, the carbon and as well as on the GPP as a part of that one, we are seeing that one the month, which is again those are the fallow period of time when there is the negative is showing which is a sink, and then the carbon sink, and then the positive is showing when the carbon releases, and these are reflecting the carbon releases around the fallow period of time. Similar thing for the Chukwal, which is a rain-fed ecosystem, which is there. The main crop is that one for us, and then as well as the rocks, and then the wheat crops are that one, and olive orchard is in our production is that one, and the same ET daily, monthly, and we are seeing again that one the value as a part of that one. Not going into my detail. Similarly, on weekly intercomparison between net primary, and here we see the other way around trend, because here it's only not an irrigated system, it's only during the winter season or whenever rainfall is at one, that's where we are seeing more variation. The rest is a bit more dormant period because not irrigated crops are happening. Irrigated crop is only the wheat crop. And looking around the water user and productivity assessment on the monthly basis, going from the top on that one, what's the maximum on the water use efficiency and how that changes over a period of time. And again, now when we are looking around the net ecosystem exchange, that's a totally different way around trend because it's not an irrigated system as a part of that one. And most of the time, the irrigated activities are only happening over a 3-month period of time. And that way we are seeing a totally different net ecosystem exchange. And it's more on that one, the carbon releases as a part of system. Moving to the Rahim Pirkha, which is on you see on this is the desert, and it's a kind of the arid agriculture system, which is cotton, wheat, and the cropping system is a part of that one. The same as the evapotranspiration changes, and what we are getting again that one, the pi subarb with flux hour ET 1143 and 1109. But when we compared with the vapor other model, then we are seeing a major differences as a part of that one. And even for this one, when we go on a daily basis daily basis, we are seeing a larger difference, even to the 15 to 20%. But when we aggregate over the annual basis or the 6-monthly basis, then we are seeing much better trend. Similarly, on the carbon fluxes for the Rahim Pirkha, again we are seeing a similar trend, April and May, which is end of Rabi season, the more carbon releases, and then the other month we see carbon sinks as a part of that one. And GPP is also showing the same. Lastly, about the Faisalabad, which is about the rice wheat belt area. And what we are saying again that the differences are a bit more on that one. The flux tower is around 823 and pi Sibal is 761. And again, we are seeing the different trend here as a part of that one in terms of net ecosystem exchange, because there is a more standing water and all sort of the processes are there as a part of that one for the rice. What that means is summarizing in the one, we are looking around the annual actual evapotranspiration for the various the 4 flux tower, and then how that variation is happening between that the flux towers across the scales, and seeing it what are the things. And again we are seeing the higher is in terms of Rahim Pirkha as a part, and when we look around the gross primary productivity, and again intercomparison between that one, that's showing a kind of the variation what. And lastly is also looking around the annual the carbon balance. Bearing in mind one thing is we are using those kind of fluxes for the UNFCCC guidelines for the because in Pakistan is at the moment is guesstimated, but utilizing this one as the first time to validate what fluxes we are getting it as a part of that one. This ET part is a one part of the project and that one, but overarching what we have been tasked by the is this is a flux tower dashboard which we have developed for various stakeholders if they want to access the data, how that could be data analyzed, and then the data could be available as a part of the final product is there, showing the different bar charts and all sort of the things of the errors and everything. And even here you could zoom into the 30 meter there closing the energy balance where you're seeing a lot of differences to the hourly, to the daily basis, day and night, and you're seeing a lot more difference in everything. Ultimately, we are working on that one, how we could go for the water accounting, which is about, we have excellent system on the groundwater monitoring system where we've installed 200 divers for monitoring the groundwater fluctuation, surface water inflow, soil moisture sensor and everything. Going for the individual to the system on the irrigation system, to the Punjab Canal Command, to the whole Pakistan, and then the Indus Basin. That's what we are looking at as a part of how that the ET output will be able to contribute and to improve the, to have a better understanding about that one. And I will be hanging around, and if there are questions, I will be happy to answer. Thank you.
Well, let's move on, right? Our next speaker is Dave Johnson. He's a principal science at Lycor. Lycor is a company that's in Lincoln, Nebraska. It's right here, right? And we collaborate with them. They're industry partners, and they actually make the eddy covariance systems. But today he's going to talk about a new sensor that they've developed, which measures ET and is going to be a lot more price friendly, right? So Dave, please, you have the floor.
Okay, yeah, when I submitted this, Christopher told me, you know, this title's a little bit long, and in hindsight, should probably just be how to accurately measure ET, and that's it. So today I'm going to talk a little bit about evapotranspiration, the computations and measurements to get at that. I'll introduce this new next generation ET sensor, and then talk about what we can learn from doing spatial measurements and some of the benefits of network sensors. And something you probably didn't know you'd see today is a reference to Coca-Cola during the presentation. So evapotranspiration, we know, is one of the largest movements of water vapor in the hydrological cycle as the water is leaving the ecosystem into the atmosphere. Of course, evapotranspiration is made from, comprised of evaporation of the water along with transpiration, all the water leaving through the vegetation. And typically we see these three terms used a lot: potential, reference, and actual ET. And so by definition, potential ET is usually what's the expected rate of ET if water is not limited. So, and it also has assumptions like, oh, the crop is green, it's completely shaded, everything's uniform height, and of course, there's a lot of water. Then we have a definition for reference ET. Here, we're also talking about an environment that is well-watered, for example, but they have some constants associated with it. But you still see some assumptions like uniform height, that it's actively growing, that it's well-watered, and it's assuming that there's no stress or no diseases or anything like that. And the FAO has put out some recommendations or procedures for looking at ET. And there's variations of the Penman-Monteith equation, which I'll talk about, but also how you can take reference ET and apply things like crop coefficients and stress coefficients to get better estimates of ET. So this Penman-Monteith model here, you can see, has about 5 different outputs to try to get an estimate at ET, and they're not always the most easy values to come at to put into this equation. So what we really want to get at is the actual ET. We've seen in the previous 2 presentations already the difference between trying to get actual numbers versus estimates here, and we want to do it based on the actual water availability, and that's a function also of the soil moisture, the species, leaf area index, climate, things like that. And if we want to use this in the hydrological and weather models for irrigation management, we really want to have accurate values for this. Just to show a couple differences here, I have about 3 slides of some examples, the difference between potential evaporation, ET, and actual. You can see it's about half in some of these instances. Here are 2 crops that were grown side by side. And you can see that even during a growing season, you have different peaks and valleys, different times of the years when the ET is actually a maximum and minimum. So it's really good to try to figure out when this is happening. This was in California at a dry grassland where basically they were going through a drought, and you could see the actual ET went down to about 0. But if you look at the potential ET, you'd be like, oh, look at all the moisture coming off this thing, and we don't need to water this grass. So, so how do we get to measuring that? This morning you heard a little bit mention of eddy covariance. So for those of you that eddy covariance might be new, basically we're measuring eddies of wind that travel across the ecosystem. And in these eddies, molecules of water vapor are carried. And as they interact with the ecosystem, these molecules come into the wind flow from transpiration and evaporation. And a very simple diagram here is as the wind carries these molecules, as the wind comes down into the ecosystem, it has a certain number of water molecules. When it comes back up, it has a different number, typically a higher number because of those 2 processes. And so what we do with eddy covariance is we measure the concentration of the water vapor as it's going in and out of the ecosystem, and we also measure the wind speed and direction as it's coming in and out of the ecosystem. And this is a data set just of 1 minute of data, and you can see how the variation of the wind speed and the H2O concentrations are changing. We're looking at how they vary, and because they're varying together, that's where the terminology covariance comes from that we're looking at. So now if we look at these equations, you can see that we have a much simpler equation. We're only looking for 2 variables to measure. These are on the same measurement system. They're in situ in the field, and we're directly measuring these molecules of water as they go in and out of the ecosystem. Also, those of you that have worked with eddy covariance systems, they can be quite complex. These are some pictures here. But a lot of these systems are used for some high research purposes. Maybe they're measuring carbon dioxide and methane and doing a lot of energy balance studies and lots of equations. So as we were trying to introduce this to irrigation management and other applications, the demands came back from the community that we want something that's low cost, low power, low maintenance, and something that we can make immediate decisions with. And so about 1.5 years ago, we introduced this new next generation of sensors. This is an ET sensor. We have it up at the booth if you want to see it in person. But basically, we're measuring the wind speed with these transducers. We have a very high precision, high speed humidity sensor inside the base, and with that, we're able to calculate ET estimates. And you can see this is what the system looks like when it's set up in the field, very simple for making these measurements. So again, we're doing ET over field scale. This is really nice for making large ecosystem measurements. We still measure it about 10 times a second because we want to capture all of these small eddies and all of these movements of water vapor. And every half hour, we give you an actual value of evapotranspiration. So these are low power. They operate on a solar panel and a battery, so you can put them up anywhere. We tried to design them so it's really low maintenance, no calibration. And the cost, I think, is the biggest thing. This is 5 to 10 times less than a traditional eddy covariance system. So it's in the neighborhood of, for example, a net radiometer, something like that. These are all the typical variables you'll see, ET, of course, and then we have things like latent energy, the sensible heat is there, vapor pressure deficit. And when we deploy these in the field, this is how a typical setup will look. And the area that you can measure with these sensors is usually about 100 times the height above the canopy of the vegetation. So let's say we put it at 7 meters above the top of the vegetation. You'll collect measurements from about 700 meters away. So it gives you an idea of what kind of scale you can do with these measurements. And they can be used agricultural crops, forests, orchards, all different kinds of applications as well. Circling back now, we can look at how do the results compare to both the potential reference ET and eddy covariance systems. And you can see in the plot here The black and the gray bars are those potential and reference ET. And you can see the dramatic difference between eddy covariance systems and this new ET sensor. And if we look at a cumulative view of that information, you can see this is just over a couple weeks, and you already have a 75% overestimation of ET if compared to what's actually being at the site. So then if we look at eddy covariance systems, which is sort of understood as the gold standard for making these types of measurements, and we compared it to the new ET sensor, you can see very good trends, similar amplitudes. The data looks really good. If we do a one-to-one relationship, it's even surprised us at Lycor. We're like 0.99, that's better than we thought. And if we do a cumulative look at the dew, this is over, I think, a month and a half, and you can see after that, the difference was about 2 millimeters. So we were really quite impressed by this performance. Now, what makes it really nice is with these kind of lower cost sensors, easy to set up, that we can start to explore spatial heterogeneity. This is the state of Nebraska where we're in today, and you can see the differences across the state. People are also interested in looking at urban or landscape level things. So we performed an experiment. We went to California and an alfalfa field there, and because these sensors are pretty easy to set up and low cost, we decided let's see how homogeneous an actual crop is. So we set 8 of these across the ecosystem with the eddy covariance system, and you can see the data there, pretty much what you would expect, all on top of each other. What's kind of interesting is that we did a cumulative look at this data, and what's kind of interesting is you see that 2 of them actually have a little bit lower ET. Now for an irrigation manager, someone like that could be useful information that maybe that portion of the field isn't getting enough water, we're getting too much water, something like that. So you can really play around with these sensors and learn a lot about things. Now I mentioned Coca-Cola, so you might not have known, but this vending machine was the very first IoT device at Carnegie Mellon back in 1982, and it would inform the owners that we need to have more Coke put in the machine because it was running empty. But now we have IoT everywhere, on our watches, on our cars, our thermostats, and everything. And this is now moving into environmental sensors and environmental measurements. Instead of just having analog outputs, sensors are becoming smart and digital and recording all this data. So at Lycor, we decided, why don't we use this new ET sensor and develop what we would call a node and use it in a term that we would call Internet of the Environment, the IOE. Okay, and so this node basically comprises of that ET sensor, then it has a module, and then we build in everything, for example, a cellular modem, the data plan, everything you see here in mounting and solar. And that whole package can then just be set up in the field in a very easy fashion. Just like the typical devices now, you scan a QR code and data immediately goes to the cloud. You don't have to set up IP addresses and go get data plans and all that yourself. We use carriers that have quite a good cellular coverage, but where there are gaps, we have the technology built in to connect into the satellite program once Musk is done doing what he's doing with the government. We often get, after this presentation, a question is like, oh, I like what I see there, ET is great, but what about carbon, right? There's a lot of questions about carbon sequestration projects, carbon credits in the market. And so we'd like to introduce this new LI720. It's a carbon flux sensor. So it's measuring both CO2 and water vapor now. We're just getting ready to start shipping this spring. You can see the form factor is more or less the same. There's a couple key differences. We're measuring now the water and the carbon at the same time. We have some built-in biomet sensors, for example, measuring photosynthetic active radiation, temperature, and relative humidity. And we're still doing all the processing on board in real time so that you don't have to do any of this downstream. We've been doing testing for a couple years now in different locations, making sure it works in hot climates, wet climates, dry climates, cold climates. And the data's looking really good. This is the CO2 data. You can see there's a little bit more noise, a little bit more uncertainty in the red data, which is from the new thing. But in the end, when you're looking at the results and doing carbon budgets and integrating under these curves, the results come out really, really good. Here's just a one-to-one relationship. So So I want to kind of wrap up the last portion here is that, you know, all through the conference here, we've been talking about providing good information to the users. And you don't want to just hand over a spreadsheet full of numbers or tell people to fix it. And so what we're trying to do is take things to the next level so people can make immediate decisions with the information they're getting. So in the cloud, we're implementing some things on that data as it comes in. For example, statistical detection of outliers, not just spikes in the data, but in between in the data during the times. And then we're applying some automated gap filling using the MDS technique and some AI and machine learning and all that. So that really takes the automation to the next level. We can then start to plot sinks and sources automatically, like you've seen in some of the presentations. What I think is really cool, you can see the gold part at the end of the chart is a forecast. So, you know, when you look at the weather and you can see the next 10-day forecast, what the highs and lows are, but now we can start to predict ET. That could be really valuable for irrigation management if farmers or growers can decide, oh, I can see how much water I'm about to lose in the next 3 to 4 days, something like that. And last here, we, you know, as we use these eddy covariance systems, I talked about the footprint that you can measure. And now we're starting to pull that data in, combine it with the satellite imagery, NDVI, other types of indices, and then we can expand from that small footprint across the whole field or across multiple fields and start taking this more to a landscape type level. So that's all I had, and I'll hang around too, Chris, and answer questions after the next speaker. But thank you.
Thank you. And the next speaker happens to be me. So I'm Christopher Deal. I'm the Director of Research of the Institute, and I'm going to talk about our Parallel 41 Flux Network. And I'm glad that Dave came before me because he's already explained eddy covariance, and I could skip those slides. In fact, the slides came from LICOR. That looks goofy, doesn't it? All right, so the Parallel 41, let me go back, see if it improves. It doesn't. There's a whole team behind this effort. As you can see, they're listed, and a lot of them are here present at this conference. Parallel 41, the concept was a network of eddy covariance flux towers to provide a real-time energy balance and ET data to measure water balance and crop water productivity. And our goal was to provide real-time crop ET for irrigation, water management, farmers, etc. here in Nebraska. Why Parallel 41? Well, I thought it was a catchy name, you know, Area 51. And Parallel 41 is the latitude that goes by southern Nebraska. And so that's our ultimate goal, is to use the data for improving spatial ET estimates from satellite. We saw Daniele already present some comparisons today, and also Mohsin. So here's where I could skip, right? Dave's already given us a lecture on eddy covariance and the measure of turbulence and eddies. And on a typical flux tower, this is what you have: a sonic anemometer measuring those wind speeds, and a CO2 and water vapor gas analyzer measuring the concentration of CO2 and water vapor. So this is what, these are some of the other instruments on a typical tower. To do the complete energy balance, we need net radiation. That's measuring the balance of incoming solar and long wave and outgoing. And then temperature, relative humidity. This project we started in 2016 with some of our own resources, and then we leveraged funds from FR. Climate Corporation donated some towers. LICOR, our industry partners, and then we partner with USDA University of Nebraska, Upper Republican NRDs, and funding from the Irrigation Innovation Consortium, and expanded the network. And the goal was to capture ET in this precipitation gradient across Nebraska. Notice that northwest 400 millimeters, southeast 900 plus millimeters, right? So if you're producing corn in this gradient, you're going to need different amounts of irrigation to complement the precip, right? So Nebraska, as you've probably learned from other talks, we're called a flyover state, right? So when you look down in the aircraft, this is some of what you see, hundreds and hundreds of center pivots, and that's the concentration of irrigation wells in Nebraska. And so we wanted to capture this ET along this gradient. So the flux towers in the network go from Iowa, which is mostly rain-fed, collaborating with John Pruger in USDA, and then with Andy Suker in Mead, Nebraska, in the university farm, and then in that gradient of precis, and also with collaborators at CSU and Kansas State. So the goal here is to measure actual ET, and we also have all the micrometeorological data to run the reference ET that David was talking about, right, with the Pema-Monteith equation. The nice thing is that Lycor developed this smart flux system, okay, which is essentially a computer on board, okay? You know, we're measuring data 10 or 20 times a second, and there's a lot of data processing that happens to transform this data into an ET value. There's a lot of corrections, coordinate rotations, etc. There's a bunch of stuff that gets done. And in the past, you would go 2 or 3 weeks, download the data to your laptop, go back and do the processing at the lab. But with SmartFlux, all that is done on board with a microchip that's running EdiPro, which is the software that the eddy covariance folks out there have developed, and to do all these corrections, and it's accepted by the scientists and researchers in the field. So, and then in addition to the SmartFlux, Lycor has the Flux Suite software. Okay, so with Flux Suite, you can log in through the cell phone modem, and you could look at the data in real time that's coming in and being processed by the SmartFlux. And you can also set quality control flags. That's really nice. If you have a tower that's out in Timbuktu, okay, and it's hard to get to, and you can set quality control that gives you a warning back, an email or a text saying, hello, something's wrong with the net radiation. Oh, darn it, a bird has pooped on it again, and we'll have to go out there and clean it, right? But the advantage is, instead of discovering that 3 weeks later, you can go and take care of it immediately and reduce your data loss, right? So here's some actual ET data, but this software is available for the tower owners, right? Not for the general public. So we created our Parallel 41 web page, and working with Lycor, they gave us access through the back door so we could download the data from their smart Flux Suite system and present it out on the web for the users and water managers, which was one of the goals, right? So you can go on there and click on a tower, picture comes up. This is our Grant, Nebraska tower, wedged in between 2 corn center pivots. And we have to measure the wind to know where the ET is coming from, right? Typically from the southeast, as you can see here. But then we present the data on the Parallel 41, and you know, you can choose inches or millimeters, right? If you're a farmer in western Nebraska, you want inches. If you're a scientist, maybe you want SI units in millimeters. So you can choose that and display the data from the last 2 weeks, reference CT and everything. And recently we got funding from the Upper Colorado River Basin Commission to expand the parallel 41 into the Upper Colorado Basin with 10 new towers. Okay, obviously Lycor are partners of ours in this. We installed 9 towers last season, and the 10th one is going to go in next week. Okay, and needless to say, it's been a logistic challenge for us to service towers in New Mexico, where it takes 2 days just to get there if you drive, right? But we've come up with solutions. Here's one of the towers on the Navajo agricultural products industry, NAPI, in northern New Mexico. Why New Mexico? Because there's a river that is in this basin, right? This basin is a river that flows into the Colorado River. So there's an example of the tower at the edge of the center pivot field. Okay, of course, center pivots and towers don't get along very well, right? So you've got to pay attention. But here's what where it is, wedged in between 2 pivots. The wind direction then comes mostly from that field on the left. Here's some of the closure, okay, that we've seen graphs in the other presentations. Looks pretty good. And some of this is another tower in Wyoming, Fort Bridger. Again, this is what it looks like when nothing is growing. Okay, again, some other shots here. Yes, we have to go in the wintertime, and sometimes it's cold, and there's snow on the ground, and that's always a challenge to service towers because you need your hands, right? And you got to take your gloves off, and it gets complicated, right? Reggiani is going like this, right? And Ashish. So here's some of the closure data again for Fort Bridger, and some of the ET we collected last year, right? So this is mostly grass hay. NAPI was alfalfa, okay? This is grass hay. And then another example of a tower is in Cora, Wyoming. So that's our furthest north tower. NAPI is our furthest south. Cora is our furthest north. Altitude, right? Different microclimate, and again, grass hay. Here's some shots. Oh, you might ask why we have all these towers with panels protecting them. Cows, exactly, cattle. Okay, we've got to protect them from the cattle because cattle love to come and rub their backs up against stuff, right? And we don't want them rubbing their backs on our towers and our equipment, right? So that's why we have the panels. Here's some data from Cora, some ET from Cora from last year. So there's a lot of processing on this data. I'm not going to get into details, but we use the EdiPro and Tovi. We reprocess the data after we get it. Reggiani and Dale are leading that effort on doing all the quality control. And we're posting this data on Ameriflux so the general public can get it eventually, right? That's the plan. Finally, our goal is to use satellite-based ET. Now, you learned about, if you were in the presentation by Sammy yesterday, about our global daily ET product using Alexi. And so I'm going to run through this real quick. We have the Alexi model, which is a 2-source energy balance model. We got daily ET. Here's some comparisons with flux towers here in Meade, Nebraska. This is at 375 meters. That's why you have a little bit of noise there. We've done comparisons in Brazil, as Sammy showed, right? And our goal then is to downscale, right, with a PIDAS Alexi to 30 meters. In real time, we have all these towers spread out, right? We have the spatial ET product is to doing daily ET, okay? And we want to anchor the spatial product with the tower data and then serve out the spatial product through an online app to the farmers so they can look at their fields and look at the daily ET spatially, and they can then see, oh, I've got a plugged nozzle. There's a ring forming in the image, right? So they can go and take care of that and look at variability in their field. So that's our goal, and we want to combine our flux tower with the remote sensing tools and close water balance in basins, and eventually in the Nile Basin, right? That's the goal. Thank you. So I invite the panelists to come up and sit down and answer questions from, you can ask any one of us some questions. We have did you lift your hand up? Would you like to go first then?
I have a question for the gentleman from Lycor. Great presentation. I'm Nebraskan by choice. Okay. I had some other opportunity, but I chose to come here. Very proud that we are among the top 3 in many areas in agriculture, mostly top 1 and top 2. And it feels very proud to see that company like Lycor exists here, and we can create world-class product. I have 3 questions for you. Pay attention. Number 1, what is the implication of ET and CO2 flux measurement for the producers? Number 1. And what is the economic viability for it? Number 3, you mentioned very good challenge about intermittent frequency of the internet. But you know, the Tesla is going to bring the satellite internet very soon. They are practicing that in India. And now it is coming to United States pretty soon. And also, you know, Meta has the Orion glass. You can get everything on your hand. You can just wear the glass and you can type on your hand in the vacuum and you can get everything there. How that is going to affect your technology? Are you already thinking about modeling those technology with the developed technology in the future, especially Orion glass? And you know Orion, right? From Meta. Oh, yeah. Orion glass from Meta. I think you know about it. And then the satellite internet. Thank you.
Okay, I guess, I don't know if this is on. But the first question, I think the value of ET and carbon data to the farmers, it depends a little bit on, I guess, the water scarcity in the market that you're doing these measurements. And in some places, like Nebraska, there's aquifer underneath, so there's a kind of plenty of water source. But as you start moving downstream, there's been a lot of debating on how much water you should be using to irrigate your farm. And typically farmers might be putting on a lot more water than they actually need because it's abundant in here. But as you move further downstream, then there's less water for the other farms. And you know, we've heard some other talks here, and it's been in the news, where you're starting to have legal issues, where you're suing different places and the water rights. And you know, there's a presentation they were paying some farms to not grow so they could use the water. And so ideally, if they can find out the right amount of water to put on and still get the same yield and everything else is excess, then that can be a benefit from the water savings, cost savings from running pumps and distributing the water, running the pivot irrigation things. From the carbon data, and I've actually seen this year quite a large explosion of groups looking at the carbon market and getting carbon credits. And I know in the US it's kind of up and down, but internationally it's becoming quite popular, where agricultural farmers can potentially get money for how they produce their crops, for example, doing tillage or not tilling and that sort of thing. And if they're able to reduce greenhouse gases in the atmosphere by having crops that take up more CO2, or, you know, with rice, they're trying to reduce methane and that sort of thing. That's another option for people as well. I think the last question was about the technology.
Economic viability. Second question. Economic viability.
Economic viability.
Economic viability of this technology to the farmers?
Well, that's where I was thinking that if you are able to, you know, the idea was an eddy covariance system is unrealistic for farmers. And even the system I just introduced today is high priced for a farmer. As Christopher explained, you're trying to find out that area where maybe this isn't something that a farmer owns, but maybe in a region where there's a lot of farmers, they might have systems like this set up where they can use that information to then decide how much water to use and kind of share that data. So I think the economics does that save them water by knowing how much the ET rates are and they're not overwatering. So I think that's probably the biggest economic value there. So. The technology is always tricky, especially nowadays. After you put a chip on a board, a month later, it's out of date. We used to have instruments that would last 20 years, and now that's not good anymore. You need to constantly update. So we have just like most companies, you have an R&D team that's always looking into the future and trying to predict what people will want, try to keep costs low, and keep things robust. So I don't know if that answers your question. Yeah.
Are your R&D team is thinking about how the Orion glass or the satellite technology for data and phone will be used in your current system?
For sure, communication. That's the biggest issue is, all these places are remote, and a lot of them, you have different carriers, and this is just in the US, much less anywhere else. India, China, they have firewalls and all kinds of things, and it's really difficult to establish communication. So that's been probably one of the biggest things we've been trying to tackle with the most recent instruments is how do people from their offices collect that data, look at that data, and have information that they can use instead of going and getting a USB drive, downloading the data, and doing it that way. So yeah, as soon as that, Starlink opens up, most phones already have that capability built in now, and it's just a matter of time before that happens. And so I think that'll open a world of opportunities for putting measurements basically anywhere on the globe and being able to take those measurements.
Francisco.
Thanks for the talks. I have a couple of questions, very brief. One question is for Professor Machine, and regarding the performance of your instruments in arid to semi-arid regions and how you overcome those, let's say, deficiencies or problems of coming with accurate measurements. And the second question is for Professor Zakaria, but I'll let you.
Thank you. We are fortunate enough in a way where we have installed the flex tower. We have a field office at those locations. Because our prior experience was that a field office is far away where this is installed, and it becomes quite tricky due to many problems, and especially the birds, any of those ones. And when we are working in the farmer's field, often the farmers start doing some of the plowing activity, and then you don't have any control. The learning from that experience was that we should be establishing the flex tower at the government site, at the university research station, where we have a control and where we have agreement that for the next 5 years, they're giving us a particularly dedicated space, and then they will be able to grow the crops based on what are our needs on that one. And then we deployed a particularly research technician who is there weekly maintenance of that one, dust and everything, plus as well as that one, the some of the flex sites as flex suit, which is guiding us if something is not working it, and then we got to know on that one, not at the field site, but also at the headquarters, and saying it, who are the relevant people. You are getting that kind of alert and saying it, oh yes, that's the problem. If I compare back to the 20 years ago, when the flex tower was installed in Ghana, in Accra, and we were working it from Germany, and it was a nightmare that you need to call, and then it 2-3 months. But now where we are in between that, in Australia, where I was working it, where it was around 800 kilometers far off, and then you needed 2 days to reach that site. And then that created a lot of problem. And I think, of course, on the passage of time, that when the technology has improved substantially, the processing and then the data query and all as the processing is moving on, then it's giving us the layers and all sort of things, outliers, what can we do and everything. And we could develop a much more robust the maintenance system. Typically, we are doing a maintenance on a bi-monthly, not on a quarterly or on a 6-monthly, to make sure that all the instruments are functioning. These are some of the way we are doing it, but nothing is perfect. Often we encounter the problem, and then we have to go on the day and fix those ones.
Thank you. Can I proceed with the second one, or
Yeah.
see if someone else is?
Go ahead.
All right, my question is, it was unclear to me whether if you were supporting or not the remote sensing products, and on the other hand, given the information that you provided to evaluate OpenET, what was your field work? Where were your locations? How many stations or places did you deploy? And if those, let's say, measurements are available, if you can provide us some more information.
So I think OpenET has a value in California, but not for perennial crops with micro-irrigation. At this point, there's still too much inaccuracy, and growers are being charged penalty fees that are somehow attributed based on inaccurate estimate. So this is creating a lot of concerns, a lot of burdens, and is pushing the commodity board to request, as they did, accuracy assessment or independent evaluation like we did. So far, we have 24 eddy covariance stations all in production fields. They were somehow, the locations were coordinated with the commodity boards. So we want to have well water and good growers, good, high yielding fields. And we pay a lot of attention on maintenance and periodic Q&A. We're doing some additional correction. One recent article came from a group of biometeorologists that requires to correct the sensible heat flux by another coefficient. But also we are scrutinizing a lot our ground data with the Bayesian analysis. Because even if you take measurement, you pay a lot of attention on the sensor and do a lot of maintenance, there is some error embedded in the ground measurement. So we are evaluating those errors, recalculating somehow a true or expected values, and then we are going to recompare with what is available from OpenET. So also the projects that we are running has an objective to suggest improvement. And so at the end of the analysis, we're going to suggest improvements. And there are a few that probably can boost up a little bit the accuracy. Yeah. Yes.
A couple of things. OpenET is free, right? And you said that the sources of error come also from observations. So at the end, those plots that you show have a combined error from the observations as well as from the model simulations. Is that correct?
Based on we did some preliminary correction, and we figured out that for citrus, the inaccuracies the discrepancy between corrected ground measurement and OpenET estimates are even larger. What I presented is before the correction, because we're doing the correction as we proceed. But the level of inaccuracy on subtropical crop, not only on citrus, it's citrus, avocado, and olive, it's alarming. And I think it comes from the assumption that those models that were developed for forage crops, mainly irrigated with sprinkler or surface irrigated, can be somehow applied everywhere. And I think California is a different planet for the cropping system. And also, there's some deficit irrigation that growers do for quality purposes. And so as you go on and increase the sensible heat flux for either drought or quality purposes, this is where remote sensing of ET loses its accuracy most of the time. Yep.
And I'm going to add a comment to this discussion. If you noticed, Dr. Mohsin also used T-ball and compared it to his towers. And it did a lot better than the data that Daniele did. And one of the reasons, in addition to the transpiration issue and the stomata closure, is C-ball and metric are one-layer models, okay? They were developed for uniform canopies, and that's just not the case with citrus and pistachios, right? Where you have exposed soil in between these bluff bodies, right? And it's just, and you notice that his results, the model that did the best was
Dual source.
well, the two-source model, right?
Yeah.
Alexei and two-source model. So there's two things happening. One, the fact that it's one-layer models, and two, the transpiration effect, right? That these things need to be adjusted.
Personally, I think that for us it's a little bit of a overstretch to push these models to provide accurate estimate on micro-irrigated perennial crop, woody crops. I think we have to go with a specific model that put at the center of the estimate the crop and not the physics around the crops. Because as I showed you, the crop reacts to, in these two cases, very sharply to BPD and not to reference ET. Everything is considered in this 7 model as very tightly linked to reference ET, and in our case, it's not.
So, do we have other questions out there? Yes, Paul. Do you want to use the mic? It's coming.
With LICAR, you have been presenting this on past conferences here, yeah, as that evolved. Where do you see this going in 5 years? The conference in 5 years, what are you going to be presenting on the sensors?
From what I've seen at other conferences and just the topics, there seems to be a big push for ground truthing, and more measurements are being made from space, and the accuracy of how those models are. I was at WMO, I think it was last September, something like that, where they're looking to put measurements, their ideal measurements are like every 100 square kilometers all around the globe of just some kind of sensors to measure what's going on with the atmosphere and the climate change and everything like that. So I see kind of more of a proliferation of lower cost instruments, sensors, this type of thing, to ground truth what's being measured from space. Water, of course, right now is probably one of the biggest factors and important things because it's tangible to people. CO2 and climate change is still kind of out there. There's people, obviously, in the government now, but there's questions on climate change and how can we start to curb the effects of what's going on, and how can we measure that? How do we know what's happening in different ecosystems? Where are the sinks and sources? There's a lot of measurements on ambient concentrations of carbon dioxide, for example, and methane and N2O, but there's not a lot of measurements on where the sources are, where the sinks are, and how big those sources and sinks are. So I think there'll be expansion in that area as well.
Go ahead.
Hi, my name is Mig. I have a question regarding the presentation about OpenET. I had a quick question about the data used for assessment. What is the quality of the data used in assessment, like the date range? Because every different ecovariance, data set have different data ranges. So to come up with that conclusion to say that the model's accuracy is not well enough, so I think that has to depend on the level of data that you use to make that assessment.
Yeah, I think I understand where you were going. So the real question is, what level of accuracy will people expect for different applications, right? So if you're a farmer and you're managing water, then that 30–50% on specialty crop might be risky because you might over-applying. So if irrigation scheduling,
then I think the level of accuracy should be pretty tight. But then you go on water allocation, water delivery, water management, where you consider some sort of buffering. So when we asked this question to different water managers, so we launched a survey actually. We didn't get a lot of responses for citrus, about 50 people responded. But when we asked that question, so what is the expected level of accuracy of ET from the satellite? And they always say, oh, the same as a flow meter, 2 to 3%. We're not there. We're never going to be there. And even if we do all the improvement that we recommend, we're not going to be there. But it's important to know what kind of what do you consider acceptable? So to me, with the cost of energy, the cost of land, and the cost of water in California, and the penalty fees that growers are paying, like $600 an acre, for apparently using too much water with respect to allocation, and everything is estimated inaccurately. This is unrealistic to me so far. So the accuracy assessment is really a little bit more articulated than what I presented, but for the sake of time, yeah.
Could you just summarize or elaborate a little bit on the role of monitoring soil moisture and application and triangulating the error? Is that a useful source of understanding, the evapotranspiration, how much water is applied and how dry the soil is, or is that useless?
In our case, in micro-irrigated crops?
In any cases?
Well, it really depends. In drip irrigated orchards and vineyards, the dynamic of soil water is not necessarily indicative of ET. So we monitor the applied water, we monitor the water consumptively used by the crop. But when it comes to soil moisture, people have tried that and they got crazy because a lot of orchards and vineyards are now grown on marginal soil. They're very spatially variable. So how many soil moisture unit you put? But I don't want it to overcomplicate. I think there's 3 different soil water balance that you have to run in micro-irrigated crop. First of all, the 2 feet deep, and then in the wet area, and then the deeper one, and then you have to run 1 for the interrow. So there are 3 levels of water, and so how you average those? I mean, no, I would say that feedback check control from soil moisture, it just to get a little bit more solid results and to make sure that ET doesn't go beyond what you apply plus what you receive from the rain. But if you want to go on the soil water dynamic, it's so complicated, and then you got salinity problem, marginal soil. I would retire now if I had to do it. Yeah.
I just want to comment on our experience. I think, yes, absolutely agree. Soil moisture dynamics is quite a complication one. Moving from 1 acre to the other acre, even from 1 meter to the next meter is varying a lot. The way we are using it, we are doing ET forecasting using the AI data mining techniques and some of the one which we, but in order to have it, ET is probably on the top of the atmosphere on the actual evapotranspiration. But when we are guiding to the farmers when they need to irrigate and how much to irrigate, in order to build some confidence for them, we have deployed around 300 soil moisture sensors. And those soil moisture sensors are 20 centimeter, 40 centimeter, and 60 centimeter. And that's giving like a traffic light diagram. If it is like a green, it means that there is enough water. If it is red, then you need to start thinking about that one. That's where it is below. And that's what we are using for farmers to build their confidence. We know what's the likely rainfall forecast. And farmer, if he's not getting irrigation water, canal water, and he wants to pump the water, and pumping has a certain cost, then we are saying that the forecasted model is telling this one, and you could look on your profile on that one, and what the 60 centimeter layer is telling us. Is that telling that you need to irrigate or not? And that could be used as a part of that for building the confidence measure. That's the way we are using it, relating the ET with the soil moisture.
Time?
Yeah.
Okay. So Bruno Lehman with Nebraska Extension. I've been trying to engage growers to do more and more irrigation, adopt any sort of irrigation scheduling tools. And then after 3 years working with one guy, and I've proved, and we ran some on-farm research, that he could save roughly an inch of water or 25 millimeters of water during the growing season. And if you do the math, and with the amount of area that he has, if he cut back 1 inch of water all across his fields, that's water that can be is sufficient water to allocate in Omaha for 3 days. Just some of the data that I've been looking and considering, say, well, that's a lot of water savings. But then still, he comes back to me and said, Bruno, the cost of technology is too high. If it's more than $10 an acre, I'm not gonna buy. And I'm like, oh man, what should we do as researchers and extension agents that would make them adopt? And when I say what should we do is on the research and development side that will make them actually start using more and more technologies.
So you asking who?
Anyone.
All right, you want to start?
Yep. I think your question is very important. I mean, our analysis is telling us again on that one, the 18% for wheat, or if for the 300 field, that 12% for maize and sugarcane. But how that, if you translate to the whole Punjab scale of the irrigated around 4.4 million hectare, then that has a lot. But then how that will, the cost of saving of that one is enormous. And how to do that economies of scale is one of the biggest challenge. Yes, you could have saving, but how that saving could be translated to the massive scale, that needs a huge infrastructure, the economy, and that's quite a challenging thing. Because typically we are working with the farmers, the extension agent, and all sort of things. How that translates towards the large scale, that's a big unknown thing yet.
Well, you want to add?
Probably not.
You don't have the answer?
You know, I have the answer, but in our situation, the advanced growers are using weather forecast to anticipate up to 7 days the reference ET. They're good to handle crop coefficient, and that they have their own adjustment from experience. But it's not for saving water at all. You know, there's no water saving in their mind. It's more economic water productivity, and for eventually lowering the energy bills, because with automation they go around the time of use for energy, and that's probably the best suitable solution, but it requires a lot of attention. Yeah.
Well, we're encroaching into the coffee break. Let's thank the panelists. Thank you all. Thank you all for coming and asking questions, and let's continue the conversation upstairs, having coffee. And then the next session is a LICOR flash talk session.